Our story begins in the aftermath of World War II. The conflict had demonstrated the growing importance of electronics in warfare, from radar to code-breaking computers. As the Cold War dawned, both the US and Soviet Union raced to develop ever more advanced electronic systems. But there was a problem. The vacuum tubes used in early computers and radios were bulky, fragile and power-hungry. Engineers dreamed of a better way to control electric currents. The answer would come from an obscure class of materials called semiconductors. In December 1947, 3 researchers at Bell Labs made a breakthrough. John Bardeen, Walter Brattain, and William Shockley had been experimenting with semiconductors like germanium and silicon. They discovered that by carefully manipulating these materials, they could create a solid-state switch, the first transistor. The transistor was a quantum leap forward. It could amplify and switch electrical signals, just like a vacuum tube, but in a much smaller package that used far less power. The implications were enormous. Shockley, an ambitious and abrasive character, soon left Bell Labs to commercialize the transistor. He set up shop in Mountain View, California, planting the first seeds of what would become Silicon Valley. But Shockley was a difficult boss, and in 1957, 8 of his top researchers quit en masse. These traitorous 8 went on to found Fairchild Semiconductor. Among them were Gordon Moore and Robert Noyce, 2 names that would loom large in the history of the semiconductor industry. Now, while Shockley and his former employees were getting Fairchild off the ground, another key player entered the scene. In 1958, an engineer named Jack Kilby joined Texas Instruments. Kilby had been pondering how to simplify the rat's nest of wires needed to connect individual transistors and other components. His solution was brilliant in its simplicity. Why not make all the components, transistors, resistors, capacitors, out of the same semiconductor material? This would allow an entire circuit to be fabricated on a single piece of silicon. On September 12, 1958, Kilby demonstrated the first working integrated circuit. It was crude by today's standards, just a few components on a sliver of germanium, but it was the start of a revolution. Meanwhile, over at Fairchild, Robert Noyce was working on a similar idea. In early 1959, he filed a patent for his own integrated circuit design. Noyce's approach used a novel, planar manufacturing process that would prove easier to mass produce. The integrated circuit, or microchip, was born. But who would buy these exotic new devices? The answer came from an unlikely source: the US government's space program. In 1961, President Kennedy committed America to landing a man on the moon by the end of the decade. This audacious goal would require radical advances in computing power. Traditional computers were far too large and heavy to fit in a spacecraft. NASA turned to the fledgling semiconductor industry. Fairchild won a contract to supply integrated circuits for the Apollo guidance computer. This infusion of government funding was crucial in helping the young company scale up production and drive down costs. The military was another early adopter. In 1962, the Air Force chose Texas Instruments to supply chips for the Minuteman II intercontinental ballistic missile. These contracts provided vital revenue and helped semiconductor firms improve their manufacturing processes. As the 1960s progressed, integrated circuits found their way into more and more applications. The first electronic calculators hit the market, followed by digital watches and early video game consoles. Each new product drove demand for more powerful and cheaper chips. In 1965, Fairchild's Gordon Moore made a prescient observation. He noticed that the number of components that could be crammed onto a chip was doubling about every year. Moore predicted this trend would continue for at least a decade. This became known as Moore's Law, though it's more of an observation than a physical law. Nevertheless, it proved remarkably accurate. For decades, the semiconductor industry used Moore's Law as a roadmap, driving relentless improvements in chip density and performance. But trouble was brewing in paradise. By the late 1960s, Fairchild was struggling with management issues. Key employees, including Moore and Noyce, grew frustrated. In 1968, they left to form their own company, Intel. Intel focused on a new type of chip called memory. Traditional computer memory used tiny magnetic rings threaded with wires. It was slow, expensive, and limited in capacity. Intel bet that semiconductor memory could do the job better. Their gamble paid off. Intel's first product, the 3101 static RAM chip, was a hit. It was followed by the 1103 dynamic RAM, which became the best-selling semiconductor device in the world. While Intel was conquering the memory market, another revolution was brewing. In 1971, Intel engineer Ted Hoff was working on a chip for a Japanese calculator company. He realized that instead of designing a custom chip for each new calculator, it would be more flexible to create a general-purpose chip that could be programmed for different tasks. The result was the Intel 4004, the world's first microprocessor. It combined the key elements of a computer: processing, memory, and input-output control, onto a single chip. The 4004 wasn't very powerful by today's standards, but it was a watershed moment. For the first time, a complete computer could fit on a chip smaller than a fingernail. The microprocessor opened up vast new markets for semiconductors. Personal computers, video game consoles, and all manner of smart devices became possible. The digital revolution was underway. But as the American semiconductor industry boomed, it faced growing competition from abroad. Japanese companies like NEC and Toshiba began producing memory chips in large volumes. By the early 1980s, they were giving Intel a run for its money. The Japanese had several advantages. Their government coordinated research efforts and provided low-interest loans. Japanese companies had a longer-term outlook and were willing to accept lower profits to gain market share. And their manufacturing quality was often superior. American chipmakers cried foul, accusing Japan of unfair trade practices. They lobbied Washington for protection. In 1986, the US and Japan signed a semiconductor trade agreement that set minimum prices for memory chips. But the writing was on the wall. Intel's profits from memory chips were evaporating. CEO Andy Grove, another Fairchild alumnus, faced a wrenching decision. Should Intel double down on memory or pivot to a new market? Grove chose to exit the memory business and focus on microprocessors. It was a gutsy move that paid off handsomely. Intel went on to dominate the PC processor market for decades. As Intel was reinventing itself, a new player entered the scene. Morris Chang, a veteran of Texas Instruments, founded Taiwan Semiconductor Manufacturing Company, TSMC, in 1987. TSMC pioneered a new business model, the dedicated semiconductor foundry. Instead of designing and manufacturing its own chips, TSMC would produce chips for other companies. This allowed small design firms to compete without the massive capital investment needed for a chip factory. The foundry model transformed the industry. It enabled a new breed of fabless semiconductor companies that focused solely on chip design. Firms like Nvidia and Qualcomm rode this wave to become powerhouses in their own right. Meanwhile, the end of the Cold War brought new challenges and opportunities. The US military, long a major customer for advanced chips, saw its budgets shrink. But a new market was emerging: mobile phones. Early cell phones used relatively simple chips. But as phones got smarter, they required more processing power. Companies like Qualcomm and ARM designed specialized chips optimized for mobile devices. The smartphone revolution created huge new demand for semiconductors. As the 21st century dawned, the chip industry faced both promise and peril. Moore's law continued to drive advances, but the physics of miniaturization was getting trickier. Each new generation of chips required massive R&D investments and ever more sophisticated manufacturing equipment. The cost of building a state-of-the-art chip factory, or fab, skyrocketed into the billions of dollars. This raised the stakes for chip makers. A misstep in technology or market timing could be catastrophic. One company that navigated these challenges with particular skill was TSMC. Under Morris Chang's leadership, it invested heavily in leading-edge manufacturing technology. TSMC formed close partnerships with equipment suppliers and customers to stay at the forefront of the industry. By the 2010 IIS, the global semiconductor landscape had shifted dramatically. Intel still dominated PC and server processors, but it was struggling to break into the booming mobile market. Memory chip production was now led by Samsung and other Asian firms. In chip manufacturing, TSMC emerged as the undisputed leader. Its fabs in Taiwan produced the most advanced processors for companies like Apple, Qualcomm, and AMD. This concentration of critical know-how in one small island would soon raise geopolitical concerns. Another rising force was China. Long content to be the world's electronics assembler, China now aimed to build its own world-class semiconductor industry. The government poured billions into subsidies and R&D. Chinese companies began buying up chip firms and poaching talent from Taiwan and elsewhere. The US government grew increasingly alarmed. Semiconductors were now seen as a strategic industry, critical for both economic competitiveness and military superiority. The prospect of China dominating chip production was viewed as a national security threat. These concerns came to a head during the Trump administration. In 2019, the US placed restrictions on selling advanced chips and manufacturing equipment to Chinese telecom giant Huawei. This was followed by broader controls on chip exports to China. The semiconductor industry found itself caught in the crossfire of a new technological Cold War. US chip companies, which counted on China for a large share of their sales, protested the restrictions. But national security hawks argued that short-term profits shouldn't outweigh long-term strategic interests. The COVID-19 pandemic added another wrinkle. As large swaths of the global economy shut down, chipmakers initially cut production. But demand for semiconductors soon surged, driven by sales of laptops for remote work and gaming consoles for homebound consumers. The result was a chip shortage that rippled through multiple industries. Automakers were particularly hard hit, forced to halt production due to a lack of electronic components. The shortage highlighted the critical role of semiconductors in the modern economy and the fragility of global supply chains. As we record this in 2023, the chip industry faces a pivotal moment. Geopolitical tensions and supply chain concerns have prompted calls to reshore semiconductor manufacturing. The US recently passed the CHIPS Act, providing $52 billion in subsidies to boost domestic chip production. But building a more resilient semiconductor ecosystem is easier said than done. The industry's success has been built on a complex web of global partnerships and specialized expertise. Duplicating this in any one country would be enormously expensive, if it's possible at all. Moreover, the physics of chip miniaturization is bumping up against fundamental limits. Moore's law, which drove the industry for so long, is slowing down. Chip makers are exploring new materials and novel computing architectures to keep performance improving. Artificial intelligence is emerging as the next major frontier. Companies are racing to develop chips optimized for AI workloads. This could reshape the competitive landscape once again. Through it all, semiconductors remain at the heart of our digital world. The average smartphone today contains more computing power than all of NASA had during the Apollo program. Data centers packed with specialized chips power the cloud services we rely on daily, and emerging technologies like self-driving cars and the Internet of Things will only increase our dependence on semiconductors. So what does the future hold for this vital industry? Will the US succeed in rebuilding its chip manufacturing base? Can Taiwan maintain its dominance in advanced chip production? And how will the rise of AI and quantum computing change the game? One thing is certain: semiconductors will continue to play a crucial role in shaping our technological future. The tiny switches etched in silicon have already transformed our world in ways that would have seemed like science fiction just a few decades ago. Who knows what marvels the next generation of chips will enable? That brings us to the end of our whirlwind tour through semiconductor history. I hope you've gained a new appreciation for these microscopic marvels that power our digital lives. If you enjoyed this episode, please subscribe to By the Victor and leave us a review. And let us know in the comments what other technologies you'd like us to explore in future episodes.